From the last two examples, we're talking about the problems. The function f of x is regular x or f of x equal to something or y equal to something. But this one, let's looking at another example where the function is y squared equal to x. This is a sideways parabola. So for this one, because of the function y squared equal to x, it's really hard to write y in terms of something x like square root of x. And we do not want to do that. So what we can do is we are going to modify our arc length formula from the a to b of square root of 1 plus dy dx squared dx. We're going to modify it to dx over dy dy. And what is that? This piece is still going to be the first derivative, but we're not going to take derivative with respect to x. We're going to take derivative with respect to y. So you can thinking about this as g of y equal to something y. And then at the end, of course, we were going to have dy instead of dx. So the function is y squared equals to x. So we can thinking this one in terms of x equal to y squared. So dx dy is going to be 2y. This is different than the implicit differentiation you learned from the Calc 1. This is different. This is a regular derivative, just thinking about y as the variable you're going to take the derivative, not x. So once we take out the y, let's move on to our arc length formula, which is going to be the y values from 0 to 1 of square root of 1 plus the dx dy squared, so 2y squared dy, which is going to be integral from 0 to 1 of 1 plus 4y squared dy. Now the setup is easy. The antiderivative, the integration is a little bit trickier because we have the formula, we have the integration square root of 1 plus 4y squared. This is actually the setup for trig substitution. So what I'm going to do, or what I'm going to think is 1 plus 4y squared. I'm going to match it with 1 squared plus 2y squared. And then according to this form, back to the trig substitution sections, we know we're going to set the quote-unquote x in terms of a tangent. But this time our x is going to be 2y equals to 1 times tangent of theta. In other words, y is equal to 1/2 tangent of theta. Then dy is going to be 1/2 secant squared theta d theta. So the whole thing now can be rewritten as integral from 0 to 1. Let us not worry about that one for right now. Square root of 1 plus 4y squared, which is now becomes to tangent square theta. dy now is going to be 1/2 secant square theta d theta. And 1 plus tangent square theta, that is secant square theta. So we ended up with secant theta times 1/2 secant square theta d theta, which is going to be 1/2 constant out secant cube theta d theta. Now we have to using integration by part for the antiderivative of secant cubed theta d theta, which is going to be 1/2 multiplied by I just directly write down the answer. Another 1/2 of secant theta tangent theta plus ln of secant theta plus tangent theta, and then we still haven't done the integration yet. Okay, so just in case you have questions about the secant cube portions, we're going to let u equals to secant theta, du is going to be secant theta tangent theta, and dv is secant square theta d theta, then v is going to be tangent theta. And then when we set up the integration by part, we will end up with integral secant cube theta d theta is equals to secant theta tangent theta minus the integral of secant tangent square theta d theta. And then we're going to using the integration by parts twice, which this side will have another we'll have another. Oh, actually, do we have to do the? We do not need to do another integration by parts, but we're going to using the identities to rewrite tangent square as secant square theta minus 1, where we will have antiderivative of secant cube, and then a derivative of secant theta, and those two together become two copies. That is this 1/2 coming from, and this one, the antiderivative of the secant, which is this portion. Okay, so that is not the focus here, so I'm going to erase it. So continue for the arc length. Now we're going to simplify them. We got 1/4 secant theta tangent theta plus ln of secant theta plus tangent theta. And then we want to integrate them. So I do not want to change back to the y's because it's a little bit too complicated. So what I'm going to do is, I know at the beginning I have y equal to 0 and y equal to 1. So when y equal to 0, tangent theta is going to be 2 times y, which is 0 again. Then for that situation, theta is going to be 0. Then when y is equal to 1, tangent theta is going to be 2 times 1, which is 2. So theta is going to be tangent inverse of 2. Now we do not know what is that theta is. But we know that secant square theta equals to 1 plus tangent square theta. So when tangent theta equal to 2, secant square theta is equal to 1 plus 2 squared, which is 5. Secant theta is equal to square root of 5. So we can plug in using those informations. So the L is going to be 1/4. Let me using different colors. So when y equal to 1 and when y equal to 0. So when y equal to 1, L is equals to 1/4 secant theta square root of 5 multiplied by tangent theta 2 plus ln of secant theta square root of 5 plus 2, which is going to be square root 5 over 2 plus ln of square root 5 plus 2 over 4. And when theta equals to 0, then tangent are equal to 0.